Hello there, and welcome to Sleepy Science Vault. Somewhere out in the vast, silent reaches of space, there exists an object so extreme, so impossibly strange, that even Albert Einstein himself struggled to accept it could be real. In the early years of the 20th century, Einstein reshaped our understanding of the universe with a single, elegant idea: that gravity is not simply a force, but a curve in the very fabric of space and time. His equations were beautiful, precise, revolutionary. And yet, when other physicists began working through the deeper implications of those equations, something troubling emerged. Buried within the mathematics was a prediction so violent, so absolute, that it seemed to break the rules of nature itself. Einstein didn't like it. Many of his contemporaries didn't either. Surely, they reasoned, the universe wouldn't actually allow something so extreme to exist. It had to be a flaw in the math, a strange mathematical ghost, not a physical reality. But the universe, it turns out, doesn't concern itself with what scientists find comfortable. Today, we call these objects black holes. And even now, with satellites orbiting the planet, with telescopes capable of capturing light from billions of years ago, with supercomputers modeling the deepest physics we know, black holes remain among the most mysterious objects ever discovered. We've confirmed they're real. We've even captured images of their shadows. And still, in many ways, they continue to defy full understanding. To understand why they unsettled some of the finest minds in scientific history, it helps to understand what a black hole actually is. Not a hole in the way we might picture one. Not an empty void quietly waiting to swallow stray planets and passing comets. A black hole is something far stranger than that. It is matter, an almost unimaginable amount of matter, packed into a space so small it barely seems possible. Picture the mass of an entire star, or in some cases, many stars combined, compressed down into a single point. Not a smaller star. Not a dense little sphere you could circle with a spacecraft and study from a safe distance. In many cases, the matter collapses all the way down to what physicists call a singularity, an impossibly tiny point where ordinary physics seems to break down entirely. The matter isn't just packed close together. It is crushed beyond any density we could ever picture in daily life, denser than rock, denser than metal, denser than the white-hot cores of other stars. And it's this almost impossible compactness, this extreme concentration of mass into so little space, that gives a black hole its terrifying strength. Gravity depends on how close you can get to an object's mass. The closer you are, the stronger the pull becomes. A black hole allows you to get closer to an enormous amount of mass than anything else in the known universe. That is the quiet secret behind its power. Not simply that it is massive, but that all of that mass is folded into so little room. This extreme density does something remarkable to the universe around it. Space and time, woven together into a single fabric scientists call space-time, begin to bend, to stretch, to curve. Around an ordinary star, space-time dips gently, the way a heavy ball might rest on a stretched sheet of fabric, curving the surface around it without tearing through. But around a black hole, that gentle curve becomes a steep, plunging well, bending more and more sharply the closer you travel, until eventually, the curvature becomes so extreme that nothing can climb back out again. Not a spacecraft. Not a wandering asteroid. Not even light. And this is the detail that makes black holes truly unlike anything else we know of. Light is the fastest thing in the universe. Nothing should be able to catch it, let alone hold it captive. And yet, near a black hole, gravity becomes so overwhelming that even light cannot escape its pull. Space curves in on itself so completely that there is no longer any path leading away, only inward, deeper, and further from everything else in existence. Black holes are the only known objects in the universe with this strange, almost unsettling ability to trap light itself. Which leads to one of the most curious truths about them. Because they swallow every photon that wanders too close, black holes do not shine. They do not glow. They emit no light of their own at all. By their very nature, they are invisible. We cannot simply point a telescope toward a black hole and see it sitting there in the dark, the way we might see a planet or a distant star. There is no surface to reflect light. No glow to catch the eye. Instead, scientists have to search for the faint clues left behind in its presence, the way nearby stars wobble, as though tugged by an unseen hand, the way background light bends and distorts as it passes a patch of seemingly empty space, the swirling disks of gas and dust that heat to extraordinary temperatures as they spiral toward a center that simply isn't there. It becomes a kind of detective work. Searching for a silhouette in the dark. Hunting for the fingerprints of something that refuses to be seen directly, and only reveals itself through the way it quietly disturbs everything around it. And yet, despite being invisible, despite defying easy detection for so much of scientific history, black holes appear to be woven into the very architecture of our universe. At the centers of galaxies, including our own Milky Way, scientists believe enormous black holes rest like silent anchors, their gravity helping to hold entire galaxies together, gently shepherding billions of stars into the slow, graceful orbits that keep a galaxy whole, rather than scattering into the dark. In a strange way, we live within the gravitational shadow of something we still don't fully understand. So where do these vast, invisible giants come from? How does a universe filled with starlight and color end up producing something so dark, so absolute? For most black holes, the story doesn't begin with darkness at all. It begins with light. It begins with a star. Stars spend most of their long lives in a careful, ongoing balance. Deep within their cores, nuclear fusion burns fiercely, pushing outward with tremendous energy, while gravity pulls inward at the same time, constantly trying to crush the star down under the weight of its own mass. For millions of years, sometimes billions, these two forces hold each other in a kind of quiet, burning equilibrium. But that balance cannot last forever. Eventually, even the largest stars run out of fuel. The fires at their core begin to dim, and without that outward pressure pushing back, there is nothing left to resist gravity's pull. And so, the star's own immense weight finally wins. In an instant, by cosmic standards, the star collapses in on itself. For the most massive stars in the universe, this collapse doesn't stop at some smaller, stable form. It doesn't settle into a new kind of star, denser but still recognizable. The core simply keeps falling inward, the matter pressed tighter and tighter together, past every threshold we might expect nature to hold steady at, until what remains is no longer a star in any sense we would recognize at all. What's left, in that final, silent moment, is a black hole. A single point in space where a brilliant, burning, living star once stood, now replaced by something so dense, so warped, that not even its own light can find a way out. And so, in the quiet death of a star, a new kind of darkness is born, one that will go on shaping the space around it for billions of years to come. When a massive star finally collapses under its own weight, it rarely does so quietly. The dying moments of a star this size are anything but gentle. As the core gives way and gravity wins its long, patient battle, the outer layers of the star are blasted outward in one of the most violent events the universe has ever produced, a supernova. For a brief window of time, that single dying star can outshine an entire galaxy, blazing with a brightness so intense it can be seen from billions of light years away. But while the outer layers of the star are hurled across space in a brilliant display of light and energy, something very different is happening deep at its center. There, in that collapsing core, matter is being crushed beyond anything we can easily picture. Atoms themselves are no longer able to hold their shape. Electrons and protons are forced together, merging under unimaginable pressure, until the core becomes denser than even the nucleus of an atom, which, until that moment, scientists considered to be about as tightly packed as matter could possibly get. And yet, for the most massive stars, even this isn't the end of the crushing. The collapse continues past that point, past every barrier physics seemed to promise would hold firm, until a black hole is all that remains. This is the most familiar origin story for a black hole, the dramatic, fiery death of a star far larger than our Sun. But it isn't the only way these objects come into existence. The universe, it turns out, has more than one method for building darkness. Sometimes, instead of a single star collapsing alone, the process begins with two stellar remnants already locked in a slow, cosmic dance. Neutron stars, the incredibly dense leftover cores of stars that have already exploded, can sometimes orbit one another for millions of years, gradually spiraling closer and closer together. Eventually, in a final dramatic moment, they collide. And under the right conditions, that violent merger produces enough mass, compressed into enough density, to form an entirely new black hole. Other times, the trigger isn't a collision between dead stars at all, but something far stranger, two living stars orbiting dangerously close to one another. When stars draw near enough to begin interfering with each other's structure, siphoning off gas, distorting one another's shape, throwing off the careful balance that keeps a star stable, the result can sometimes tip one of them past the point of no return, sending it collapsing inward long before it otherwise would have. And then there's a third path, one that doesn't begin with stars at all. Once a black hole exists, it doesn't necessarily stay alone. Two black holes, drawn together by gravity across unimaginable distances, can slowly spiral toward each other over millions, sometimes billions of years. When they finally meet, they don't simply collide and shatter. They merge. Two separate black holes become one, larger and more massive than either had been before, releasing a final, thunderous ripple of energy across the fabric of space-time itself, a wave so subtle by the time it reaches us that it took scientists more than a century after Einstein's first predictions to actually detect one. These mergers can happen again and again, in a kind of slow cosmic chain reaction. A black hole formed from one merger may eventually drift close enough to another black hole to merge once more, growing larger with each encounter. In dense stellar environments, scientists have even found evidence suggesting that three black holes can become entangled together, circling one another in a complex gravitational dance, before two of them merge first, leaving the third still orbiting what remains, until perhaps, given enough time, all three become one. It's a strange thought to sit with. That somewhere out there, in the quiet dark between galaxies, black holes might be slowly finding one another, drifting closer over spans of time too vast for a single human life to witness, merging, growing, and reshaping the gravitational architecture of the universe in ways we are only just beginning to detect. With so many different paths leading to their creation, it shouldn't be surprising that black holes don't all come in the same size, or behave in exactly the same way. In fact, scientists have come to recognize an entire family of black holes, different in scale, different in origin, yet all sharing that same fundamental nature. As far as we currently understand, there are 4 distinct types. Some of the strangest, and perhaps the most elusive, may have formed before stars even existed at all. In the first fractions of a second after the Big Bang, the universe was an extraordinarily chaotic place, dense, searingly hot, and far from the smooth, orderly cosmos we observe today. Tiny irregularities, slight variations in density scattered throughout that early universe, may have been significant enough in certain pockets to collapse directly into black holes, without ever needing a star to form and die first. Scientists call these primordial black holes, and if they exist, they would be relics from the very beginning of time itself, silent witnesses to the birth of everything, older than any star, any galaxy, any light we have ever observed. Within that same theoretical family, there's the possibility of something even smaller, miniature black holes, some perhaps no larger than a single atom, yet still carrying mass within them. These tiny black holes, if they truly formed in those first fleeting moments after the Big Bang, would behave nothing like the dramatic, star-devouring giants we tend to imagine. They would be quiet, unassuming, almost impossible to detect. And yet, tucked within their impossibly small frame, they would still obey all the same strange rules, bending space, trapping light, existing as tiny, hidden knots in the fabric of the universe. Whether these primordial and miniature black holes actually exist is still one of the open questions in modern astrophysics. No one has confirmed one beyond doubt. But the possibility alone is enough to expand our sense of just how strange, and how varied, the family of black holes might truly be, stretching from objects smaller than anything we could ever see, all the way up to forces so vast they shape the structure of entire galaxies. And this is only the beginning of that story. Because beyond the stellar black holes born from dying stars, and the theoretical primordial black holes from the universe's earliest moments, there are other members of this family still waiting to be explored, black holes so large, so impossibly massive, that they make even these origins seem small by comparison. Not all black holes are created equal. Within this extraordinary family of objects, there exists a range of scales so vast it almost defies comparison. From the smallest confirmed black holes, barely heavier than a handful of suns, to objects so immense that our ordinary language begins to feel inadequate, the spectrum is genuinely staggering. The most common type, the ones scientists have confirmed in the greatest numbers, are known as stellar mass black holes. These are the direct descendants of massive stars, born in the fires of a supernova and carrying the remnant mass of whatever star gave rise to them. They typically range from around 5 times the mass of our Sun upward, through tens of solar masses, and sometimes beyond. In cosmic terms, these are the more modest members of the family. Not small by any ordinary measure, but comprehensible at least as a concept, the collapsed remains of a single star, dense and dark, drifting through space. Then there are the giants. Supermassive black holes exist at the other end of the scale entirely, and the difference in size between these and their stellar cousins isn't like comparing a pebble to a boulder. It's more like comparing a grain of sand to a mountain range. Supermassive black holes can contain millions or even billions of times the mass of our Sun, and they appear to sit at the hearts of most large galaxies in the observable universe, including our own. Among all the black holes ever observed, one stands in a category almost entirely by itself. In a galaxy far beyond the edges of the Milky Way, there sits an object known as TON 618. It is, by current measurements, the largest confirmed black hole ever detected. Its mass is estimated at somewhere around 66 billion times the mass of our Sun. The number is so large it stops feeling like a measurement and starts feeling more like a concept, a kind of placeholder for something our minds were never really built to hold. The event horizon of TON 618, that invisible boundary beyond which nothing can return, stretches across a distance larger than our entire solar system by an enormous margin. Our Sun, our planets, the long elliptical orbits of the outermost bodies in our neighborhood, all of it would fit comfortably inside that boundary, with room to spare. TON 618 doesn't orbit a galaxy. It is the anchor of one, a gravitational presence so overwhelming it organizes everything around it simply by existing. And yet, on the other end of the known spectrum, there is something almost endearing in its contrast. The lightest confirmed black hole ever measured carries a mass of around 3.8 times that of our Sun. It sits right at the edge of what physics currently allows a black hole to be. Any lighter, and the collapsing matter might not have enough mass to push past the boundaries that would normally stabilize it into a neutron star instead. But somehow, this one made it across. The smallest known member of the family, holding its place in the cosmos just barely, quietly bending space-time on a scale far more modest than its distant relatives. Between the stellar and the supermassive, there is supposed to be a middle ground. A category of black holes carrying masses somewhere between a few hundred and a few 100,000 solar masses, the intermediate black holes. In theory, they should exist. The mathematics allows for them. The evolutionary pathways that could produce them seem plausible. And yet, confirmed examples have proven remarkably difficult to find. A handful of candidates have been identified over the years, objects that seem to behave in ways consistent with intermediate mass, but none have been pinned down with the same certainty as their larger or smaller cousins. It's one of the quieter mysteries in modern astrophysics. If black holes form across such an extraordinary range of sizes, why does this middle tier seem so hard to find? Are intermediate black holes genuinely rare? Are they simply difficult to detect with current instruments? Or are they hiding in places we haven't looked carefully enough yet? The questions remain open, and the search continues. What is no longer in question, however, is just how widespread black holes are across the universe. For a long time, they were considered exotic oddities, extreme objects that existed somewhere out in the cosmos but played no particular role in the broader structure of things. That picture has changed completely. It now appears that virtually every large galaxy in the observable universe harbors a supermassive black hole at its center. Not just the unusual ones. Not just the most dramatic or visually striking galaxies. Most of them, including galaxies that look perfectly calm and ordinary from the outside. Somewhere near the middle, anchoring everything quietly, sits a black hole with a mass that dwarfs anything in the surrounding stellar population. Our own galaxy is no exception. At the center of the Milky Way, roughly 26,000 light-years from where our solar system makes its slow orbit, there sits a supermassive black hole known as Sagittarius A star. It carries a mass of around 4 million times that of our Sun, and it has almost certainly been sitting at the heart of our galaxy for billions of years. For most of that time, scientists didn't know it was there. It took decades of careful observation, tracking the movements of stars near the galactic center as they swung through tight, rapid orbits around something invisible, before the evidence became impossible to ignore. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, a glowing ring of superheated gas curling around an absence in the center, marking the shadow of a black hole that had been there long before our planet even formed. It was a quiet, extraordinary moment in the history of science. A photograph of something once considered invisible by definition. And yet, Sagittarius A star is just one of a staggering hidden population. Our galaxy alone is estimated to contain millions of black holes of various sizes, scattered across its spiral arms and drifting through its halo. Most of them are completely undetectable with current technology. They produce no visible light. They're not actively feeding on nearby material in a way that would generate a signal we could observe. They simply exist in the dark, warping space around them in ways too subtle to notice from a distance. There could be a black hole within a few light-years of our solar system and we might not know it. The darkness between stars isn't empty. It's populated, in ways we're only beginning to understand, by objects that reveal themselves to nothing, absorbing whatever drifts close enough while giving away as little as possible in return. It's a humbling thought. We live within a galaxy that we have been studying for centuries, mapping its stars, tracing its arms, learning its structure piece by careful piece. And still, folded into that familiar spiral, hidden in the quiet between everything we can see, there are millions of black holes we cannot find. Waiting. Bending space. holding their silence in the dark. There is something quietly unsettling about the idea that the universe contains millions of black holes we will simply never find. Not because we haven't tried hard enough, or because our instruments aren't sensitive enough yet, but because the nature of these objects makes true indivisibility possible in a way that almost nothing else in science does. Most of the black holes in our galaxy are drifting through regions of space with nothing nearby to disturb, nothing to feed on, nothing to announce their presence. No glowing accretion disk. No cluster of frantic stars wheeling around a common center. Just empty-looking space, curved slightly inward around a point that reveals itself to no one. The honest truth is that we will probably never map most of them. We will never know their exact locations, never chart a complete census of the black holes sharing our galaxy with us. That gap in our knowledge isn't a temporary problem waiting to be solved by the next generation of telescopes. It may simply be a permanent feature of the universe we inhabit, a place where vast numbers of the most extreme objects ever formed exist beyond our ability to find them, scattered across distances we can measure but never meaningfully cross. What we can do is work with what the universe occasionally chooses to show us. And sometimes, just close enough to be remarkable, it does. The nearest confirmed black hole to our solar system is an object known as Gaia BH1. It was identified using data from the European Space Agency's Gaia mission, a spacecraft designed to map the positions and movements of stars across the galaxy with extraordinary precision. What the data revealed, in this particular case, was a star behaving oddly, moving in a way that only made sense if something massive and invisible was pulling on it. The culprit turned out to be a black hole sitting roughly 1,500 light-years from Earth, making it the closest confirmed black hole we have ever found. 1,500 light-years sounds like a safe distance. And in practical terms, it is. Gaia BH1 poses no threat to our solar system whatsoever. But as a matter of cosmic perspective, it is our nearest neighbor of this kind. In a galaxy roughly 100,000 light-years across, containing hundreds of billions of stars and potentially millions of black holes, the closest one we've confirmed sits just 1,500 light-years away. That's not the far edge of the galaxy. It's practically the same neighborhood. And if the nearest known black hole sits 1,500 light-years away, the most distant one yet identified sits at the almost incomprehensible opposite extreme. There are black holes we have detected at distances of over 13 billion light-years from Earth. When we observe them, we are not seeing them as they are now. We are seeing light that left them 13 billion years ago, when the universe itself was still in its earliest chapters. These are objects that formed not long after the Big Bang, when the cosmos was young and chaotic and stars were burning with a ferocity that the universe has never quite matched since. To look at these distant black holes is to look back through nearly the entire history of time. The light arriving at our telescopes today began its journey when our solar system didn't exist. When Earth didn't exist. When the atoms that would eventually become you and everything around you were still scattered across young, newly forming galaxies, far from any arrangement that resembled life. Somewhere in that ancient, distant light, recorded faithfully by our instruments, is the signature of a black hole that was already enormous before our world was even born. The range between Gaia BH1 and the most distant detected black holes spans almost the entire observable universe. And somewhere between those two extremes, hidden in the dark, are millions more we may never account for. Which raises the obvious and fascinating question: if black holes are invisible by definition, absorbing every photon that comes near enough, how does anyone find them at all? The answer is that scientists learned long ago not to look for the black hole itself, but for the story it tells on everything around it. The first object ever seriously proposed as a black hole candidate wasn't identified by imaging it directly, or by detecting some unique radiation it produced on its own. It was identified by the extraordinary behavior of its surroundings. The object known as Cygnus X1 first drew scientific attention in the early 1970s when it was detected as one of the brightest X-ray sources in the sky. X-ray astronomy was still a young field at the time, and the detection of such powerful, high-energy radiation coming from a single point in space immediately suggested something unusual was happening there. What astronomers eventually pieced together was a picture of a black hole in a binary system, locked in a gravitational partnership with a large, luminous companion star. Material from that companion star was being steadily drawn toward the black hole, spiraling inward in a flattened disk of superheated gas that glowed brilliantly in X-ray wavelengths before disappearing past the point of no return. The black hole itself remained invisible. But the chaos it caused in the matter around it, the tremendous energies released as that infalling gas was compressed and heated, produced a signal loud enough to cross thousands of light years and register in our earliest space-based detectors. Cygnus X1 taught scientists something fundamental. If you want to find a black hole, don't look for the absence of light. Look for the excess of it. Because a black hole actively consuming nearby material creates one of the most energetic environments in the universe, and the radiation produced by that process can be detected from extraordinary distances. This insight opened an entire field of black hole detection built on the observation of accretion disks. When a black hole sits close enough to a source of gas, dust, or stellar material, that material doesn't fall straight in. Angular momentum causes it to spiral, gradually orbiting at higher and higher speeds as it moves closer to the event horizon. As it spirals inward, particles collide, friction builds, temperatures climb to millions of degrees, and the disk begins to radiate. Not just invisible light, but across the full electromagnetic spectrum, including the high-energy X-rays that gave Cygnus X1 away decades ago. An actively feeding black hole surrounded by a bright accretion disk is, in a beautiful irony, one of the most luminous objects in the universe. The same force that traps everything inside the event horizon drives an enormous release of energy just outside it, as infalling matter surrenders its potential energy in a brilliant, swirling display before crossing the final boundary. Some black holes, particularly the supermassive ones at the centers of distant galaxies, are surrounded by so much infalling material that they outshine everything else in their galaxy combined. These are what astronomers call quasars, blazing beacons from the early universe that announced themselves to our telescopes long before we fully understood what we were seeing. But not every black hole is actively feeding. Most stellar mass black holes drift alone through space, with no companion star nearby and no pool of available gas to draw in. For these isolated black holes, silent and dark, a different technique is needed. One that relies not on the radiation they produce, but on the gravity they cannot hide. Everything with mass bends the fabric of space-time, and light, traveling along the curves of that fabric, follows paths shaped by the mass it passes near. Around a black hole, those curves are dramatic. When light from a distant star or galaxy passes close to a black hole lying between us and that background source, the black hole acts as a kind of natural lens, bending and amplifying the light around it in predictable ways. The background object appears to brighten and shift. Sometimes it splits into multiple images. Sometimes it forms a perfect ring of light around the dark center. This phenomenon is called gravitational lensing, and it offers scientists a way to detect isolated black holes that would otherwise leave no signal whatsoever. By monitoring vast populations of stars and watching for the characteristic brightening patterns that indicate something massive and dark has drifted across the line of sight, astronomers can pick out the signatures of black holes that have nothing around them to reveal their presence in any other way. It's painstaking work, requiring years of data and careful statistical analysis, but it has already led to confirmed detections and hints at a hidden population far larger than direct observations alone would suggest. Then there is the method that doesn't rely on light at all. When two massive objects orbit one another, they ripple the fabric of space-time. These ripples, called gravitational waves, travel outward from their source at the speed of light, growing fainter and fainter as they spread across cosmic distances. For decades after Einstein's general relativity first predicted their existence, gravitational waves were considered essentially undetectable. The distortions they cause in space-time by the time they reach Earth are incomprehensibly small, stretching and squeezing the distance between objects by a fraction far smaller than the diameter of a single proton. And yet, in September 2015, instruments sensitive enough to detect exactly that kind of distortion picked up a signal. Two black holes, each carrying tens of solar masses, had spiraled together over millions of years, finally merging in a fraction of a second and releasing a burst of gravitational energy that passed through our planet like a gentle whisper through an ocean. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, recorded it. And when scientists analyzed what they had found, they recognized immediately that they were looking at something historic. It was the first direct detection of gravitational waves. The first confirmed observation of two black holes merging. And the first time humanity had detected anything using a force other than light, a new way of listening to the universe that opened an entirely new field of astronomy almost overnight. The universe had been speaking through gravitational waves for billions of years. We had simply never had ears sensitive enough to hear it. But perhaps the most striking moment in the long human project of understanding black holes came in April 2019. For all the detections, all the inferred observations, all the mathematical certainty that black holes exist and are real and sit at the centers of galaxies, no one had ever actually seen one. Not directly. Not in the way you could look at a photograph and say, there it is. That changed with the work of the Event Horizon Telescope, a collaboration linking radio telescopes spread across multiple continents into a single, planet-sized instrument of extraordinary resolving power. The target was Messier 87, a giant elliptical galaxy some 55 million light-years away, known to harbor a supermassive black hole at its center with a mass around 6.5 billion times that of our Sun. The team spent years collecting data, processing petabytes of information, and assembling the result into a single image. When that image was released to the world, it showed something simple and yet profound. A bright, glowing ring of orange and red light, warped into an asymmetric curve, surrounding a dark circular region at its center. The dark region was the shadow of the black hole. The ring was the glow of the accretion disk, bent and amplified by the extreme gravity, wrapping partially around the black hole before escaping toward us across 55 million light-years of space. It was blurry. It was imperfect. But it was real. And for a species that had spent decades debating whether black holes truly existed in physical reality rather than merely in mathematics, there was something quietly extraordinary about having an actual photograph to look at. For the first time in history, humans knew what a black hole looked like. Not as an equation. Not as a computer simulation. Not as an artist's rendering built from theory and imagination. As an image. As evidence. As a thing in the universe that had been observed directly, its shadow captured by a network of instruments and preserved as a picture that anyone could see. The scientists who built and operated that telescope wept when the image finally resolved. Some of them had spent decades of their careers working toward that single moment, never entirely certain it would be possible. And in the quiet, slightly blurry orange ring of that first photograph, all of those years of uncertainty resolved into something much simpler. Something that even the most skeptical scientist, working in any field, could understand at a glance. It was there. It had always been there. And now, at last, we had seen it. There is a boundary in space that has no physical surface, no wall, no visible marker of any kind. You could pass through it without feeling anything unusual, without any instrument alerting you, without any sudden change in the light or the temperature or the stars visible ahead of you. And yet, crossing it would be the most final act in the universe. There would be no returning. No signaling back. No possibility, under any circumstances, of reversing what had just happened. This boundary is called the event horizon, and it is the defining feature of every black hole ever studied. Not the singularity at the center, not the accretion disk, not the gravitational lensing visible from a safe distance. The event horizon is the threshold that separates the rest of the universe from a region where the ordinary rules of escape simply no longer apply. To understand why nothing can cross it and return, it helps to think about escape velocity. Every massive object in the universe requires a certain speed to escape its gravitational pull. To leave the surface of Earth and never return, you need to reach roughly 11 kilometers per second. For the Sun, that number is much higher. For increasingly dense and massive objects, it rises further still. A neutron star, already extraordinarily compact, requires a significant fraction of the speed of light to escape from its surface. A black hole takes this concept to its absolute limit. At the event horizon, the escape velocity required to pull away from the black hole's gravity equals exactly the speed of light. Not almost the speed of light. Not nearly. Exactly. And since nothing in the universe can travel faster than light, nothing that crosses that boundary can gather enough speed to climb back out. The mathematics is clean and absolute. Once inside the event horizon, every possible path through space and time curves inward. There is no trajectory, no direction, no choice of movement that leads anywhere other than deeper in. This is what makes the event horizon so different from every other gravitational boundary in the universe. It isn't simply that escape would be difficult. It isn't that you would need an enormously powerful engine, or an extraordinary amount of fuel, or some technology far beyond our current capabilities. It's that escape is geometrically impossible. Space-time itself curves inward so completely past that point that the concept of outward no longer meaningfully exists. Every direction, including what would seem intuitively like a way, curves back toward the center. Inward is the only option. Inward is the only future. In this sense, a black hole is something genuinely unlike any other structure in nature. It is a one-way membrane woven into the fabric of space-time. Matter, energy, light, information, everything that crosses the horizon becomes, in a very real physical sense, lost to the rest of the universe. Not temporarily. Not in a way that might be undone by some future discovery or technological advance. Permanently and completely, as far as any outside observer will ever be able to determine. Black holes are, in the most literal possible reading of the phrase, tombs of matter. Whatever falls in is contained forever, sealed behind a boundary it can never cross in the other direction. The atoms that once formed a star, the light that once lit up a galaxy, the information encoded in the structure of any object that wanders too close, all of it passes through the event horizon and is cut off from the rest of existence as completely as if it had never been there at all. And the isolation is total. It isn't simply that you couldn't physically escape if you somehow found yourself inside a black hole. It's that you couldn't even communicate with the universe you left behind. No signal of any kind, light, radio waves, gravitational waves, any form of energy or information we have ever identified, can travel from inside the event horizon to outside it. The same physics that prevents matter from escaping also prevents any message from getting through. You could know the most extraordinary things, having passed through the event horizon and traveled inward. You could witness phenomena that no scientist has ever seen. And none of it would ever reach another mind, because nothing you produced could make it back across that boundary. A black hole doesn't just trap you physically. It disconnects you from the rest of the universe at a fundamental level, severing every possible channel of communication, severing the very possibility of shared information across that divide. In a cosmos built on the transmission of light and signal and influence across vast distances, a black hole is the one place where that transmission simply stops. For many people, this disconnection is the quality that unsettles them most deeply, even more than the crushing gravity or the destruction at the center. There is something in the human experience that finds meaning in connection, in the ability to reach outward, to send something of ourselves across distance. The event horizon removes that possibility entirely and without negotiation. But the strangeness doesn't end at the boundary. Even approaching a black hole from the outside, before crossing any threshold, the universe begins to behave in ways that challenge everything ordinary human experience teaches us about how reality works. Time slows down. Not as a metaphor. Not as a poetic way of describing an intense or absorbing experience. Physically, measurably, demonstrably, time itself passes more slowly in stronger gravitational fields. This is one of the predictions that emerged directly from Einstein's general relativity, and it has been confirmed many times over at modest scales. Clocks aboard GPS satellites, orbiting at altitude where Earth's gravity is slightly weaker, run fractionally faster than clocks on the ground. The difference is tiny but real, and the GPS system has to account for it to maintain accuracy. Gravity and time are not separate features of the universe. They are deeply connected, and what bends one bends the other. Near a black hole, this effect becomes extreme. As you approach the event horizon, time dilation grows in proportion to the gravity. An observer watching from a safe distance, far from the black hole, would see your clock running slower and slower as you fell inward. Your movements would appear to decelerate. Your signals, if you were transmitting them, would arrive stretched and redshifted, their frequency lowered by the energy cost of climbing out of that gravitational well. From your own perspective, falling inward, everything might seem normal. Your clock ticks at the same rate it always has. Your heartbeat, your thoughts, the passage of seconds as you experience them, all feel unchanged. But from outside, you appear to slow to a crawl, approaching the event horizon more and more gradually, your image growing redder and dimmer as the light from you struggles harder and harder to escape. At the event horizon itself, from the perspective of an outside observer, something extraordinary appears to happen. Time appears to freeze entirely. A person falling into a black hole would seem, from the outside, to stop right at the edge, their image frozen in place, reddening infinitely as the light from that final moment struggles futilely against the gravity pulling it back. They would never appear to cross it. Their frozen image would persist, growing dimmer and dimmer, until it faded beyond detection. But they would never, from an outside viewpoint, be seen to disappear through that threshold. From the perspective of the infalling person, of course, the situation is entirely different. They cross the event horizon in finite time, feel no particular boundary, and continue inward. But they can never communicate this fact to anyone watching from outside. The two perspectives are permanently separated. What one observer sees and what the other experiences become irreconcilable, and neither is wrong within its own frame of reference. This conflict between perspectives, this fundamental irreconcilability of what different observers witness depending on their position relative to a black hole, is one of the deepest and most argued over puzzles in modern physics. It isn't just a strange quirk to file away and forget. It strikes at the heart of questions about the nature of information, the relationship between quantum mechanics and gravity, and what it truly means for something to exist or to happen. But if the event horizon is strange and final and absolute, what lies beyond it is stranger still. As matter falls inward past the event horizon, it continues falling. There is no stable orbit possible inside a black hole, no way to remain in place, no equilibrium to settle into. the inward pull doesn't weaken. It strengthens. Everything continues to compress, to accelerate, to fall deeper toward the center. And at the center, according to the equations that describe a black hole, is the singularity. The singularity is the point, or in the case of a rotating black hole, the ring, where all the infalling matter is ultimately compressed. And the mathematics describing it are deeply troubling to physicists, not because they predict something dramatic, but because they predict something impossible. At the singularity, the equations of general relativity produce what are called infinities. Infinite density. Infinite curvature of space-time. Numbers that grow without bound, exceeding any meaningful physical quantity. In physics, an infinity in your equations is almost never a discovery about nature. It is almost always a sign that your theory has been pushed into a regime where it no longer applies, where the framework you're using to describe reality has reached the edge of its validity and broken down. When an infinity appears, it usually means a more complete theory is needed, one that would replace the infinity with something finite, something real, something that doesn't require the universe to actually contain a point of infinite density. General relativity, which describes gravity beautifully across enormous scales, breaks down at the singularity. It stops producing meaningful predictions. It can no longer tell us what happens there, what the conditions are, what physical laws govern the behavior of matter and energy at that point. The theory that gave us the black hole in the first place cannot follow us all the way to the center. And quantum mechanics, the framework we use to describe physics at the smallest scales, where uncertainty is fundamental and particles exist in superpositions of states, doesn't seamlessly extend to describe a singularity either. The two greatest theories in modern physics, each enormously successful within its own domain, fail to reconcile with each other precisely where reconciliation matters most, at the center of a black hole, and at the moment of the Big Bang. This is what physicists mean when they say the laws of physics break down at the singularity. Not that the universe becomes lawless in some poetic sense. Not that anything and everything becomes possible in some fantastical way. It means our best, most carefully tested descriptions of how reality works cease to provide answers. The mathematical tools we rely on return nonsense. And beyond that point, we are, at least for now, genuinely without a map. Whatever is truly happening at the singularity, whatever a complete theory of quantum gravity would eventually reveal about the conditions there, remains unknown. Some physicists believe the singularity is a real feature of the universe, a genuine point of infinite density that nature somehow permits. Others believe it is a signal that our current theories are simply incomplete, and that a future understanding would smooth the infinity into something finite and describable. Some speculate that the singularity might represent a boundary condition of reality itself, a place where space-time as a continuous structure breaks apart into something fundamentally different, something for which we don't yet have adequate language or mathematics. What everyone agrees on is this: a black hole is not simply an object that is very heavy and very dense. It is a place where the universe, as we understand it, encounters its own limits. Where the frameworks we have built to describe reality, tested and refined over centuries of scientific work, reach the edge of what they can describe and fall silent. For a species that has built so much knowledge, mapped so much of the cosmos, explained so many phenomena that once seemed completely mysterious, there is something humbling about that silence. A black hole doesn't just trap matter and light. In a very real sense, it traps our understanding, holding it at the threshold and refusing to let it pass all the way through. The universe contains places that remain, at their very cores, genuinely beyond the reach of everything we currently know. And in the quiet dark at the center of a black hole, somewhere beneath the frozen moment of the event horizon and past the point where time itself loses its ordinary meaning, those limits are not theoretical. They are absolute, patient, and waiting. For all the certainty science has built around black holes, confirming their existence, measuring their masses, photographing their shadows, detecting the gravitational waves from their mergers, there remains a boundary that knowledge itself has not yet crossed. We understand the event horizon from the outside. We can describe the singularity mathematically, even if that mathematics eventually breaks down. But what lies between those 2 points, what actually exists and occurs inside a black hole, remains one of the most genuinely open questions in all of physics. The honest answer, offered not as an admission of failure but as a statement of where the science currently stands, is that we don't fully know. We have theories. We have competing frameworks and thought experiments and mathematical models that each capture something plausible about the interior. But confirmed, testable knowledge about what it is like inside a black hole is something we do not yet possess, and may never possess in any direct sense. The information, as we explored earlier, cannot get out. And so the interior remains, in a very real epistemological sense, shielded from us. What we can do, and what physicists have done with considerable creativity and rigor, is reason carefully about what should happen to any object that makes the crossing. And the picture that emerges depends very much on which black hole you happen to fall into. This is not an intuitive result. You might reasonably assume that all black holes, sharing the same fundamental nature, would present the same experience to anything falling through their event horizons. But the physics turns out to be more nuanced than that, and the differences are significant enough to completely change the character of what an infalling observer would encounter. Consider a supermassive black hole, one of those giants sitting at the center of a galaxy, carrying billions of solar masses within its event horizon. For an object falling towards such a black hole, including a human being, the crossing of the event horizon might be entirely unremarkable. Not dramatic. Not violent. Not even perceptible in any direct way. This seems strange at first. The event horizon is the point of no return, the absolute boundary beyond which nothing escapes. How could crossing it feel like nothing? The answer lies in the relationship between the size of a black hole and the strength of its tidal forces at the horizon. Tidal forces are what you experience when gravity is pulling more strongly on one part of you than on another, when the difference across your body is large enough to matter. Near a small, dense object, tidal forces can be enormous even at relatively large distances. But around a supermassive black hole, the event horizon is so far from the central mass, stretched across such an enormous radius, that the difference in gravitational pull across a human body at that boundary would be negligibly small. You would feel nothing unusual. No special sensation. No alarm. Just open space, perhaps the glow of the accretion disk somewhere distant, and the stars ahead still visible, still sending their light toward you. You would have crossed the most absolute threshold in the universe, and you would not feel it happen. What would follow is harder to say. You would continue falling inward. The tidal forces would eventually grow. There would come a point, closer to the singularity, where even inside a supermassive black hole, the difference in gravity across your body would become significant, and then extreme. But the event horizon itself, for a sufficiently large black hole, is not the violent boundary intuition suggests. Stellar mass black holes are a different matter entirely. These smaller, denser black holes carry their enormous mass within a far more compact event horizon, and this compactness means the tidal forces at and near the horizon are not gentle at all. For a human body, or any extended object, approaching a stellar mass black hole closely enough to cross the event horizon, the difference in gravitational pull between the near side and the far side of your body would be catastrophic long before the horizon was reached. The near side of you, facing the black hole, would experience stronger gravity than the far side. That difference would stretch you along the direction of your fall, pulling you longer and thinner, while simultaneously the gravity pulling you inward from the sides would compress you laterally. The effect continues, becomes more and more extreme, until any structured object, any atom bonded to any other atom in any configuration, can no longer maintain its integrity against the differential pull. The result, described in one of astrophysics' more vivid pieces of technical language, is called spaghettification. The object is stretched along its falling axis and compressed from the sides, drawn out into an increasingly long, thin strand of matter, pulled apart at every structural seam until what was once a coherent object becomes a thin stream of particles and plasma spiraling inward. The atoms themselves are not destroyed by this process, but every structure they form, every bond, every arrangement that gave the object its shape, is torn apart by the simple fact of falling through an unequal gravitational field. It is one of the most complete destructions imaginable, achieved without any explosion, without any collision, purely through the geometry of curved space becoming too extreme to accommodate the existence of extended matter. This is the fate that awaits anything approaching a stellar mass black hole too closely. Long before the event horizon is crossed, the object ceases to exist in any recognizable form. It becomes a thin, bright thread of superheated matter, stretched across the final spiral inward, its energy eventually joining the accretion disk or falling silently past the threshold. But here, in the comparison between the smooth crossing of a supermassive event horizon and the violent destruction near a stellar mass one, physics has not finished offering surprises. Because in recent decades, a different and deeply unsettling question has emerged about what actually awaits anything that crosses an event horizon, any event horizon, regardless of the black hole's size. The question is called the firewall paradox, and it arises not from classical physics but from the intersection of quantum mechanics with what we know about black holes. The details are technical, but the core tension is this: quantum mechanics places strict rules on what can happen to information. Information, in the physics sense, the precise description of the state of every particle in a system, cannot simply be destroyed. It must be preserved somewhere, in some form, even if it is scrambled beyond any practical recovery. This principle is called the conservation of information, and it is considered one of the most fundamental rules of quantum mechanics. Black holes, on the other hand, seem to simply swallow information and trap it behind the event horizon forever. This created a theoretical conflict, known as the black hole information paradox, that occupied some of the best minds in theoretical physics for decades. Stephen Hawking, who had earlier discovered that black holes slowly emit radiation and therefore aren't truly permanent objects, spent much of his later career wrestling with the question of where the information goes. The firewall paradox emerged as one proposed resolution to this deeper problem, and its implications are startling. Some theoretical frameworks suggest that preserving information requires something dramatic to happen at the event horizon: a wall of intense, high-energy radiation, a firewall that would incinerate anything attempting to cross from the outside. Not gradually, not through spaghettification, but instantly, in a violent burst of energy at the very threshold. If the firewall hypothesis is correct, the smooth, unremarkable crossing that physics once suggested awaited anything falling into a large black hole would not be smooth or unremarkable at all. The event horizon would be a wall of fire, an abrupt and total end, leaving nothing to continue falling inward. This is an extraordinary claim, and it remains deeply controversial. Not all physicists accept it. Many find the firewall paradox troubling precisely because it seems to force a choice between two principles that both appear fundamental: the equivalence principle of general relativity, which predicts the smooth crossing, and the conservation of information in quantum mechanics. Something in our current understanding must be incomplete or wrong. But which part, and how, remains unresolved. Some theorists have proposed a still more radical alternative, one that reframes the nature of black holes so completely it sounds more like philosophy than physics at first encounter. The proposal is that black holes might be best understood as holograms, that all the information about everything that has ever fallen into a black hole is somehow encoded on the two-dimensional surface of the event horizon itself, the way a hologram encodes a three-dimensional image on a flat surface. In this picture, a black hole is not so much a three-dimensional volume of trapped matter as it is a surface, an information-storing boundary, where the universe keeps a record of everything that has approached it. The interior, in some versions of this idea, may not be a separate physical region at all in the conventional sense. What looks like falling inward might, from a different theoretical perspective, be better described as information being encoded on a surface. This is quantum gravity territory, the frontier where our two greatest physical theories strain against each other and neither quite wins. No version of this idea has been definitively confirmed. No version has been definitively ruled out. They remain among the most active and contested areas of theoretical physics, because they touch something deeper than the specific question of what happens inside a black hole. They touch the question of what space, time, and information fundamentally are. It is worth pausing with that for a moment. In trying to understand what happens when you fall through a black hole, physicists have ended up asking whether the interior of a black hole exists as we conventionally imagine it, whether information is truly indestructible, whether space-time is perhaps a kind of emergent structure built on something more fundamental that we haven't yet identified. One object in the sky, one extreme concentration of mass, has pulled an entire civilization's worth of intellectual effort toward questions at the very edge of what human minds have yet been able to answer. And if you harbored any hope, practical or fantastical, that a black hole might offer some exotic shortcut across the cosmos, a tunnel through space-time, an escape route from ordinary physics, the picture painted by current understanding is not encouraging. Even setting aside the spaghettification, the firewall, the information paradox, and the singularity, the geometry of a black hole makes it extraordinarily poor transportation under any scenario currently considered physically plausible. Anything falling in is falling toward a singularity. The mathematics of traversable wormholes, theoretical tunnels connecting distant regions of space-time, requires conditions that appear to be either impossible or so exotic that no known physics could create or maintain them. A black hole is not a door. It is an ending. A beautiful, strange, profoundly informative ending for both matter and our theories of nature, but an ending nonetheless. Having followed matter this far into darkness, it seems natural to assume that black holes are entirely passive in their destruction, that they simply sit and consume and trap. But this assumption misses something essential about their nature. Because black holes do not only take, they also act on the space around them in ways that are active, ongoing, and genuinely extraordinary. Every black hole in the universe, without exception, is spinning. This isn't an incidental detail. It follows directly from the physics of how black holes form. Stars rotate, and when a rotating star collapses, its angular momentum, the physics quantity that measures the extent and speed of its rotation, is conserved. Just as a spinning ice skater pulls their arms inward and spins faster, a collapsing star sees its rotation accelerate dramatically as its size shrinks. The resulting black hole inherits that rotation and carries it forward, essentially forever, since there is no friction in empty space to slow it down. Some black holes spin slowly. Others spin at extraordinary rates, their surfaces approaching a significant fraction of the speed of light. The maximum spin a black hole can achieve is constrained by physics, a limit beyond which the mathematics suggests the event horizon would effectively vanish, producing what theorists call a naked singularity, a condition that most physicists believe the universe conspires to prevent. But within that limit, the range of spin rates across the black hole population is enormous. And a spinning black hole doesn't merely sit in space and pull things inward. It does something far stranger. It drags space itself along with it. This effect, predicted by general relativity and confirmed observationally, is called frame dragging, or more technically, the lens stirring effect. As a massive object rotates, it doesn't just curve the space around it. It pulls that space into rotation with it, creating a swirling, twisting distortion that spreads outward from the black hole like a vast, invisible whirlpool. In the region immediately surrounding a spinning black hole, called the ergosphere, space itself is being dragged along in the direction of the black hole's spin so powerfully that it becomes impossible to remain stationary relative to the distant stars. Even traveling at the speed of light in the opposite direction of the spin wouldn't be enough to hold still. The flow of space is simply too strong. Everything in the ergosphere is carried along whether it chooses to be or not, swept into rotation by the sheer fact of the black hole's spinning existence. This sounds almost mythological, the idea of space itself being twisted into motion by a massive spinning object. And yet it is physics, confirmed by careful measurement of the behavior of objects orbiting rotating bodies. Around Earth, the effect is tiny but detectable. Around a rapidly spinning black hole, it dominates everything within the ergosphere, reshaping the paths of orbiting matter and light into complex, precessing spirals that carry the signature of that powerful rotation embedded in their geometry. The ergosphere is also, remarkably, a region where energy can be extracted from the black hole itself. A process proposed by physicist Roger Penrose suggests that under the right circumstances, an object entering the ergosphere could split into two parts, with one part falling inward past the event horizon and the other escaping outward with more energy than the original object brought in. The extra energy comes from the rotational energy of the black hole itself, slowing its spin very slightly in the process. In principle, a sufficiently advanced civilization with access to a rapidly spinning black hole could exploit this mechanism as an energy source of almost incomprehensible power, drawing on the angular momentum of a black hole the way you might draw current from a battery, except the battery contains more energy than entire solar systems could generate over their lifetimes. This is speculation, of course, in the practical sense. But it illustrates something important about black holes that the simple picture of a consuming void fails to capture. A spinning black hole is not a passive object. It is a dynamic structure, an engine of angular momentum, actively reshaping the geometry of the space around it, participating in the mechanics of its environment in ways that go far beyond simply pulling matter inward. The universe, it turns out, did not build its most extreme objects to be merely destructive. It built them to be active, to interact with surrounding space in ways that feed energy back outward, that twist the geometry of the cosmos around them, that leave their signatures on the orbits of stars and the paths of light across vast distances. A black hole consumes, but it also spins. And in that spinning, it reaches outward in its own quiet way, stirring the space around it, twisting the fabric of the universe into patterns that carry its presence long past any distance from which the black hole itself could be directly observed. They are not holes in the universe. They are engines. Silent, ancient, spinning engines, anchoring galaxies, distorting time, bending light, and turning space itself into something that moves. The ergosphere is one of the strangest regions in the known universe, and yet by the standards of what surrounds a spinning black hole, it is only the beginning of the story. Recall that the ergosphere forms in the space just outside the event horizon of a rotating black hole, a region where space itself is dragged into motion by the spin of the object at its center. Anything entering this zone is swept along in the direction of rotation whether it wants to be or not. Even light, traveling at the maximum speed the universe allows, cannot hold a stationary position against that current. The geometry of space in the ergosphere has been bent not just inward, as around any massive body, but sideways, twisted into a vortex that pulls everything it contains into a shared rotation with the black hole itself. This twisting, dragging, rotating environment immediately outside the most extreme objects in the universe turns out to be far more than a curiosity. It is, in a very real sense, one of nature's most powerful engines. Because while matter falling into a black hole from any direction eventually passes through the event horizon and is lost to the rest of the universe, matter interacting with the ergosphere can behave very differently. Some of it gets redirected, accelerated, and then launched back outward with an almost incomprehensible amount of energy. The mechanisms behind this are rooted in complex magnetohydrodynamics, the physics of conducting fluids and plasmas interacting with powerful magnetic fields in extreme gravitational environments. As gas and dust spiral inward toward a supermassive black hole at the center of a galaxy, they form an accretion disk, that flattened, superheated structure glowing across the electromagnetic spectrum as friction and compression drive temperatures into the tens of millions of degrees. Magnetic field lines thread through this infalling plasma, anchored in part to the rotating black hole and in part to the surrounding disk, and as the system spins, those field lines are twisted and wound up like an enormous electromagnetic spring. The energy stored in those twisted fields, combined with the rotational energy extracted from the black hole through processes related to the ergosphere, eventually finds a release. And it does so in one of the most dramatic ways nature has ever devised. Some of the most massive black holes in the universe launch twin beams of plasma outward from their poles. Not outward in all directions, not as a diffuse wind blowing gently away from the accretion disk, but as tightly collimated, focused jets of particles and energy, fired in opposite directions perpendicular to the plane of the disk, traveling at a significant fraction of the speed of light. These are called relativistic jets, and they are among the most powerful continuous phenomena in the observable universe. The word relativistic here carries real weight. It doesn't mean fast in the ordinary sense. It means fast enough that the effects of special relativity become important in describing the motion of the particles involved. At those speeds, mass and energy blur into each other, time dilates, and the physics governing behavior diverges sharply from anything in everyday experience. Relativistic jets can extend for extraordinary distances. Some stretch for tens of thousands of light years beyond the galaxy that houses the black hole launching them, plowing through the thin gas of intergalactic space, depositing enormous amounts of energy into the surrounding environment. They can be detected in radio waves, in X-rays, sometimes in visible light. They are bright enough to be observed across billions of light years, and in some cases they are the dominant feature of an entire galaxy as seen from the outside. The black hole at the center of the galaxy Messier 87, the same object whose shadow was photographed by the Event Horizon Telescope in 2019, is not only remarkable for its mass. It is also the source of one of the most studied and photographed relativistic jets in the sky. The jet streaming from its center extends for roughly 5,000 light years, a beam of plasma and energy launched by a black hole and traveling at close to the speed of light, crossing a distance so vast that if our entire solar system were placed at one end, you would need to travel for 5,000 years at the speed of light to reach the other. The energy involved in producing and sustaining a structure like this is almost beyond meaningful description. The black hole itself, through its rotation and the dynamics of its accretion disk, is continuously converting some fraction of infalling mass into pure energy and redirecting it outward along those polar beams. This is not a one-time event. It is an ongoing process, sustained for millions of years, driving two enormous columns of relativistic plasma through the surrounding galaxy and out into the wider cosmos. And this brings us to one of the most energetic classes of objects ever observed. A quasar is, at its core, a supermassive black hole that is feeding actively and furiously, surrounded by an accretion disk so vast and so luminous that it outshines every star in its host galaxy combined. The name itself is a contraction of quasi-stellar object, a term coined when these sources were first detected in the mid-20th century and appeared, through early telescopes, to look like stars, compact and bright, despite being located at enormous cosmological distances. What astronomers were actually seeing was the radiation from an accretion disk surrounding a black hole carrying anywhere from hundreds of millions to many billions of solar masses, consuming surrounding matter at tremendous rates and releasing the resulting energy across nearly every wavelength of light simultaneously. Quasars can be detected from distances exceeding 13 billion light-years. The most luminous among them pour out more energy than a trillion suns. The relationship between black holes and quasars reframes something fundamental about how we think of these objects. A black hole is not simply a passive consumer, a void that takes things in and silences them. An actively feeding black hole of sufficient mass becomes one of the most radiant objects in the universe, a lighthouse visible across nearly the entire observable cosmos, powered by the conversion of matter into energy as it spirals into oblivion. The efficiency of this process is remarkable. Nuclear fusion, the process that powers stars and represents humanity's best hope for clean energy at scale, converts roughly 0.7% of mass into energy. The accretion disk around a black hole, depending on the geometry and the spin of the black hole, can convert between 6 and 40% of the mass of infalling matter into energy before it ever crosses the event horizon. A quasar is therefore not just brighter than a star. It is more efficient than a star, extracting a far greater fraction of available energy from the same amount of matter. Now consider what it would mean to be anywhere near one. The radiation environment around a quasar is not hostile in the way extreme cold or vacuum is hostile. It is hostile in the way standing inside a nuclear detonation is hostile, except sustained across distances measured in light years, and spanning the full range from radio waves to gamma rays. At close range, the X-ray and gamma-ray flux alone from a luminous quasar would deliver a lethal radiation dose in a fraction of a second, long before any other effect of the environment had time to act. There would be no shielding material known to science that would offer meaningful protection at the distances where this radiation is intense. The jets themselves, those collimated beams of relativistic particles, represent another order of danger entirely. A particle of plasma traveling at close to the speed of light carries kinetic energy that dwarfs any projectile in ordinary physics. A relativistic jet is not something you would sense approaching. It would be traveling so fast that by the time any information about its proximity could reach you, it would already have arrived. The jet from Messier 87 has enough energy to sterilize every planet within a significant radius simply by existing, by the continuous deposition of its energy into the surrounding medium over millions of years. These are not theoretical extremes invented to illustrate a point. They are the actual measured properties of objects we have photographed and cataloged. The universe built these structures, and the universe does not appear particularly concerned about whether anything could survive near them. Among the phenomena that feed a black hole's growth, perhaps the most dramatic is the event known as a tidal disruption event, the moment when a star wanders too close to a black hole and doesn't survive the encounter. A star passing at a safe distance from a black hole feels the gravity, adjusts its path into a curve, and continues on its way, perhaps forever altering its trajectory but otherwise intact. But a star that comes close enough, within what is known as the tidal disruption radius, encounters a gravitational difference between its near side and far side large enough to overcome the internal gravity holding the star together. The star is pulled apart, its material stretching outward toward the black hole in a long, thinning arc, while some portion of the disrupted mass falls inward and some is flung outward on hyperbolic trajectories. What follows is a sudden, brilliant flare as the infalling stellar material hits the accretion disk or forms a new one, releasing an enormous burst of energy across X-ray and optical wavelengths that can briefly outshine the entire host galaxy before slowly fading as the feeding rate drops off. Astronomers have now observed dozens of these events, watching in real time as entire stars, objects that burn for millions or billions of years, are consumed over the course of weeks and months. For the black hole, a tidal disruption event is essentially a meal. Depending on the mass of the star and the mass already contained in the black hole, one such event might add a small but real fraction to the total. And over cosmic timescales, black holes grow through exactly this kind of accumulation: one disrupted star, one swallowed gas cloud, one captured stellar remnant at a time. The growth of a black hole is, in this sense, patient work. There are no sudden dramatic jumps in mass under ordinary circumstances, no single event that doubles or triples the total in a brief moment, with the exception of a major merger with another black hole. Instead, there is a long, slow process of accretion, of drawing in surrounding material, feeding from the gas and dust that orbits in the galactic environment, occasionally capturing a star that drifts too close, and steadily, over millions and billions of years, growing larger. The supermassive black holes we observe at galactic centers today, the ones carrying billions of solar masses, did not arrive at those sizes overnight. They grew through an extended history of feeding, probably aided by mergers in the early universe when galaxies were colliding and coalescing more frequently than they do today. The enormity of their current masses is the accumulated record of an unimaginably long history of consumption, growth, and the quiet, relentless work of gravity drawing matter ever inward. And as they grow, their influence expands. A more massive black hole warps a larger region of space-time. Its ergosphere is bigger. Its relativistic jets, if it is spinning and feeding actively, carry more energy. Its gravitational influence extends further into the surrounding galaxy, shaping the orbits of stars at greater and greater distances. In this way, the growth of a black hole is not only about the black hole itself. It is about the growing reach of its influence over everything around it. The black hole and its galaxy are, in this sense, not separate entities. They are partners in a long, slow, gravitationally intimate relationship, each shaping the conditions the other evolves within. The black hole feeds from the gas the galaxy provides. The jets from the black hole heat and drive gas outward, sometimes suppressing star formation across the entire galaxy. The mass of the central black hole correlates in measurable ways with the properties of the galactic bulge surrounding it, a correlation so consistent that it cannot be coincidence. Whatever the full story of this relationship turns out to be, it is clear that the black hole at the center of a galaxy is not an isolated anomaly. It is a central participant in the life of the structure that contains it, consuming, growing, launching energy outward, and shaping the galaxy's evolution over timescales that dwarf the history of our planet. These objects do not simply sit in the dark and wait. They are active. They are dynamic. They feed and grow and reach outward with jets of plasma moving at nearly the speed of light, lighting up the surrounding universe with energy drawn from the most extreme physical conditions nature has ever produced. And still, for all this activity, for all the radiation and the jets and the tidal disruptions and the slow, patient growth, most of what a black hole does remains quiet. Most of the mass it has consumed is simply gone, held behind the event horizon in silence. Most of the stars it has torn apart have left no monument beyond a brief flare and a slight increase in a number too large to picture. The universe's most powerful engines are also, in most of their existence, the universe's most silent objects. Burning with activity when they feed. Dark and still when they don't. Anchoring galaxies in the quiet between meals, spinning slowly in the dark, waiting for the next star to drift a little too close. Of all the misconceptions that have attached themselves to black holes over the decades, the most persistent and perhaps the most understandable is the idea that they are cosmic vacuum cleaners, roaming the universe and hungrily consuming everything in their path. It is an image that has appeared in countless science fiction films, television programs, and popular descriptions, and it is almost entirely wrong. The fear behind the image is not entirely irrational. A black hole is an object from which nothing can escape once it crosses the event horizon, and the human mind, quite reasonably, extrapolates from that fact to imagine something that relentlessly draws in everything around it, reaching outward across space to pull stars and planets and passing spacecraft to their doom. But this extrapolation misunderstands something fundamental about how gravity actually works. Gravity does not change its behavior based on what kind of object is doing the attracting. A black hole and an ordinary star of the same mass produce identical gravitational effects at identical distances. There is nothing special about the gravity of a black hole when observed from far away. It follows the same inverse square law that governs the attraction between any two masses anywhere in the universe. Double the distance, and the gravitational force drops to a quarter of its strength. The fact that a black hole has an event horizon from which nothing can escape does not extend that point of no return outward across space. The event horizon sits close in, at a radius determined by the mass of the black hole, and beyond that boundary, gravity behaves exactly as it does around any other massive object. To make this concrete, consider a thought experiment that physicists have used for decades to illustrate the point. Imagine that our sun were somehow replaced, instantly and completely, with a black hole of identical mass. Setting aside the obvious consequences for sunlight and warmth, which would be catastrophic for life on Earth in their own right, What would happen gravitationally to the planets of our solar system? Nothing is the answer. Nothing at all. Earth would continue in exactly the same orbit it follows today. Mars would continue in its orbit. Jupiter, Saturn, Neptune, every planet and moon and asteroid and comet in the solar system would carry on moving along precisely the same paths they have always followed, because the gravitational force acting on each of them from the center of the solar system would be identical to what it is right now. The mass hasn't changed. The distance hasn't changed. Therefore, the gravity hasn't changed. What would change is the temperature. Without the sun's light and heat radiating outward, the solar system would grow cold with extraordinary speed. Earth's surface temperature would plummet within weeks. Within a year, most of the atmosphere would begin to freeze and settle to the ground. The oceans would freeze. The planet would become a dark, frozen rock, still dutifully orbiting the black hole at the center of the solar system in a perfectly stable orbit, for billions of years into the future, going nowhere. This thought experiment captures something important. A black hole is not a consumer of space. It is a concentration of mass. Its gravitational influence is real and enormous, but it is bounded. Matter that is not on a trajectory to cross the event horizon will not suddenly find itself drawn in simply because a black hole is nearby. The solar system, orbiting a hypothetical solar mass black hole, would not spiral inward over time any more than it spirals inward around the sun today. Orbital mechanics doesn't care whether the central mass is a burning star or a black hole. The numbers are the same, that insistent that it cannot be coincidence. This matters because it reshapes the emotional register with which we should approach these objects. Black holes are not hunters. They are not searching the cosmos for prey. They are extraordinarily extreme concentrations of mass sitting in specific locations, warping space-time around them in dramatic ways, but only consuming matter that actually falls toward them through the normal operation of gravity and orbital dynamics. The rest of the universe goes about its business, entirely unaffected by the existence of a black hole that isn't nearby. The second great misconception is related to the first, and perhaps even more deeply embedded in popular culture. The idea that a black hole might serve as a doorway, a portal to some other region of space-time, another universe, another dimension, another time, has proven extraordinarily resilient. It appears in science fiction with remarkable consistency, and it carries an obvious romantic appeal. The most extreme object in the universe, the place where physics breaks down, surely must open onto something new. The honest answer, based on everything we currently understand, is that black holes are not portals. They are physical objects, extraordinary ones, but objects with an interior and a singularity and a set of physical conditions that, as best we can determine, lead to destruction rather than passage. The singularity at the center is not a gateway. It is the point where our best physical theories stop producing meaningful predictions, which is a very different thing. Theoretical solutions to Einstein's equations do permit the existence of structures called wormholes, tunnels in space-time connecting distant regions of the universe or even separate universes in some formulations. Some of these mathematical solutions, known as Einstein-Rosen bridges, are superficially related to the mathematics describing black holes. But a traversable wormhole, one that anything could actually pass through and survive, requires conditions that appear to be either physically impossible or so exotic that no known process could create them. It would require what physicists call exotic matter with negative energy density, a concept with no confirmed physical realization. The wormholes permitted by the mathematics are either not traversable, collapsing too quickly for anything to pass through, or require energy conditions that nature appears unable to provide. A black hole, as it actually exists in the universe, does not connect to anywhere else. It connects inward, toward a singularity, toward the breakdown of the frameworks we use to describe nature. Whatever lies beyond that breakdown, whatever a future theory of quantum gravity might eventually describe, there is no current reason to believe it involves passage to another location. The romanticism of the portal idea is understandable, but it asks the universe to be stranger in a specific, convenient way, and the universe has its own ideas about strangeness that don't always align with our preferences. What black holes do offer, however, is a different kind of window into the hidden structure of reality. Not a portal in space, but a kind of amplifier of physical effects too subtle to detect under ordinary conditions, making phenomena visible that would otherwise be completely undetectable. And nowhere is this more powerfully illustrated than in what has happened over the past decade in the field of gravitational wave astronomy. When two massive objects orbit each other, they disturb the fabric of space-time around them. They create ripples, distortions in the geometry of space that travel outward in all directions at the speed of light, growing fainter as they spread across cosmic distances. These gravitational waves carry information about the masses and motions of the objects that produced them, encoded in their frequency and amplitude the way a sound carries information about what made it. Einstein predicted this in 1916. For the better part of a century, it remained an untested prediction, not because anyone doubted it, but because the distortions produced by any gravitational wave source reachable by our instruments were so extraordinarily small. Even the merger of two stellar mass black holes, an event releasing more energy in a fraction of a second than our Sun will produce across its entire lifetime, creates a distortion in space-time by the time it reaches Earth that is smaller than the diameter of a proton. Detecting it requires not just sensitive instruments but instruments of a sensitivity that seemed almost preposterous when first proposed. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, was built to do exactly this. Its design uses laser beams traveling back and forth along arms several kilometers long, measuring the distance between mirrors at each end with a precision that still seems barely believable. When a gravitational wave passes through the detector, it stretches one arm and compresses the other by an amount almost incomprehensibly small, and the interference pattern of the laser light changes in a way that can be detected and analyzed. In September 2015, LIGO recorded the first confirmed gravitational wave signal. Two black holes, one carrying roughly 36 solar masses and the other around 29, had been spiraling toward each other for an immense span of time, their orbit decaying as gravitational waves bled energy away from the system. In their final moments, they accelerated toward each other in a rapid, spiraling plunge, merged into a single black hole of around 62 solar masses in a fraction of a second, and released the equivalent of 3 solar masses worth of energy as a burst of gravitational waves. That burst traveled roughly 1.3 billion light-years across space, arrived at Earth as an almost imperceptible ripple in the fabric of space-time, and was recorded. The signal lasted less than 2 seconds. The distortion it caused in LIGO's arms was roughly 1,000th the diameter of a proton. And from it, scientists were able to extract an extraordinary amount of information: the masses of the 2 black holes, their distance from Earth, the approximate direction they lay in the sky, and confirmation of a prediction that had stood untested for nearly a century. It was the opening of a new sense for astronomy. For all of human history, our knowledge of the universe had been built almost entirely on light in its various forms: visible light, radio waves, X-rays, infrared radiation, all of it electromagnetic. Gravitational waves are something entirely different. They are not electromagnetic radiation. They are not affected by the matter they pass through. They travel through galaxies, through clouds of gas and dust, through the entire observable universe without being scattered or absorbed or altered. They carry information that light cannot, from events that light might never reveal, and they arrive at our detectors with their content intact after journeys of billions of years. The universe has been generating gravitational waves since its earliest moments, and we have only just learned to listen to them. Since that first detection, the catalog of gravitational wave events has grown steadily. Black hole mergers, neutron star mergers, and combinations of the two have been recorded. Each event adds a data point to our understanding of black hole populations, mass distributions, merger rates, and the underlying physics of these extreme systems. The data tells stories that no other method of observation could access. And the scale of activity the data reveals is staggering. When scientists combine gravitational wave observations with theoretical models of black hole formation and merger rates across the observable universe, the numbers that emerge suggest that black hole mergers are not rare, exceptional events scattered sparsely across cosmic history. They are happening constantly, throughout the universe, at a rate that, when integrated across all the galaxies in the observable cosmos, amounts to something in the range of hundreds of thousands of mergers every year. Consider that for a moment. Not just 1 or 2 black hole mergers occurring somewhere in the universe during a human lifetime. Something closer to 800,000 or more annually, each one releasing more energy in its final moments than the sun will produce in its entire life, each one sending ripples through space-time in every direction, each one quietly reshaping the black hole landscape of whatever galaxy it occurs in. Most of these are too distant to detect individually with current instruments. Their gravitational wave signals arrive at Earth too weak and too overlapping with other signals to be cleanly resolved. But collectively, they contribute to what physicists call a gravitational wave background, a kind of constant, low-level hum of space-time distortions produced by the accumulated mergers of black holes and neutron stars throughout the observable universe. Detecting and characterizing this background is one of the next major goals in gravitational wave astronomy, and the methods being developed to do so involve arrays of pulsars, rapidly spinning neutron stars spread across our galaxy, used as a natural detector of long-wavelength gravitational waves with arm lengths of thousands of light-years. Even the more modest act of two stars orbiting each other generates gravitational waves. Not at amplitudes detectable by our current instruments in most cases, but real and present, slowly draining energy from the orbital system and causing the two stars to gradually spiral toward one another over timescales that can span millions or billions of years. This process was confirmed indirectly decades before LIGO's first detection, through careful timing of a binary pulsar system whose orbital period was observed to decrease at exactly the rate predicted by general relativity's gravitational wave emission formula. The physicist Russell Hulse and astronomer Joseph Taylor were awarded the Nobel Prize in Physics for this work, a Nobel Prize for confirming the existence of something they never directly detected. Gravitational wave astronomy is still in its infancy. The detections recorded so far represent the very beginning of what will likely become a rich and comprehensive catalog of the universe's most violent events, each one a data point and a growing picture of how black holes form, how they evolve, how common they are, and how they shape the galaxies they inhabit. Future detectors, including space-based interferometers with arm lengths of millions of kilometers, will be sensitive to gravitational waves from supermassive black hole mergers, from the earliest moments of the universe, and from sources we haven't yet imagined. For now, what we have is enough to appreciate the scale of what has changed. We live in a universe where black holes are not exotic curiosities found only at vast, safe distances. They are the sites of ongoing, continuous, dramatic physical events, hundreds of thousands of mergers every year, each producing a burst of energy and a ripple in space-time that passes through everything in its path, including our planet, including our bodies, without resistance and without announcement. The universe is restless. It has always been restless. And we are only now, with these extraordinary instruments and the physics to interpret what they hear, beginning to understand just how much has been happening in the dark all along. For all that gravitational wave astronomy has revealed in its brief existence as a field, the discoveries have done something that great scientific breakthroughs often do. They have answered certain questions with extraordinary precision while simultaneously sharpening and deepening the questions that remain. Every confirmed merger, every measured mass, every mapped distance has added detail to a picture that, on closer inspection, contains more unexplained features than the rougher sketch it replaced. Scientists working with gravitational wave data have identified 5 broad categories of mystery that persist even after years of detections and analysis. 5 areas where the data either reveals something unexpected or simply declines to provide the answers the models predicted. Together, they represent the current frontier of black hole physics, the edge where understanding ends and genuine uncertainty begins. The first concerns the mass distribution of the black holes being detected. When physicists built theoretical models of how stellar mass black holes should form from collapsing stars, those models made predictions about the range of masses the resulting black holes should carry. And the observations have largely confirmed those predictions across a certain range. The vast majority of black hole mergers detected by gravitational wave observatories involve black holes with masses below roughly 43 times that of our Sun. That number, 43 solar masses, appears repeatedly in the data as a kind of upper boundary for the most commonly observed systems, consistent with what we understand about which stars can collapse directly into black holes of various sizes. But this consistency, satisfying as it is within its range, immediately raises a question at both ends of the spectrum. At the lower end, the lightest black holes remain stubbornly difficult to detect. The boundary between a neutron star, the densest stable object physics allows, and the lightest possible black hole is not cleanly mapped by current observations. There exists a range of masses, somewhere between roughly 2.5 and 5 solar masses, where the data goes quiet. Objects in this range are neither confidently identified as neutron stars nor as black holes. Whether this gap in the observed population represents a true absence of objects at those masses, a genuine feature of how stellar collapse works, or simply a detection limitation of current instruments, is a question current data cannot definitively resolve. At the upper end, a different puzzle emerges. Mergers involving black holes with large differences in mass between the two partners, what physicists call asymmetric mergers, appear to be underrepresented in the observed catalog. Theoretical models allow for mergers between a very massive black hole and a much lighter companion. Such events should produce distinctive gravitational wave signatures. But confirmed detections of strongly asymmetric mergers have been relatively rare, rarer than naive expectation might suggest. Whether this reflects something about how black hole binary systems form and evolve, or whether it reflects observational limitations, remains an open question. Which leads naturally to the second major mystery: where do the binary black hole systems being observed actually form in the first place? A binary black hole system is two black holes orbiting each other closely enough that their orbit decays through gravitational wave emission on a timescale short enough to produce a merger within the age of the universe. Forming such a system requires two massive stars to have lived their entire lives, evolved, and collapsed into black holes while remaining gravitationally bound to each other throughout that process. This is not straightforward. Stars in binary systems interact with each other as they evolve, exchanging mass, influencing each other's structure, potentially disrupting the binary when one of them explodes as a supernova and receives a velocity kick that could break the pair apart. Several formation channels have been proposed. Some binary black holes may form from pairs of massive stars that were born together in the same stellar nursery and remained bound through the deaths of both. Others may form dynamically in dense stellar environments, like globular clusters, where black holes that formed independently can encounter each other, lose enough energy through gravitational interactions with surrounding stars to become bound, and eventually spiral together. A third possibility involves the early universe, when conditions were different and star formation proceeded differently, potentially producing binary black hole systems through pathways unavailable today. Each of these channels predicts slightly different distributions of masses, spins, and orbital orientations. By carefully measuring these properties across the growing catalog of detected mergers, physicists hope to eventually disentangle the contributions of different formation mechanisms. But with current data, the mixture remains unclear. Most mergers observed could be consistent with more than one formation pathway, and the question of which channel dominates remains genuinely open. The third mystery concerns time itself, or more precisely, how the rate of black hole mergers has changed across cosmic history. The universe today is very different from the universe several billion years ago. Galaxies were younger and more active. Stars were forming at higher rates. The density of matter was higher, and collisions and mergers between galaxies were more frequent. All of these factors would affect how often black hole binaries formed and how quickly they merged. Understanding how the merger rate has evolved over cosmic time would reveal something important about the relationship between black hole formation and the broader history of the universe. It would tell us whether we live in an era of relatively high or low black hole merger activity, and how the black hole population we observe today compares to what existed in the early universe. But mapping this evolution requires detecting mergers at cosmological distances, identifying events that occurred billions of years ago, and building a statistical picture of how rates have shifted. Current instruments can reach far enough to make a start on this, but not far enough to map the full history. That will require the next generation of gravitational wave detectors, more sensitive instruments capable of detecting mergers across a much larger volume of space and time. These 5 areas of open questions in gravitational wave astronomy are, in one sense, the focused, technical edge of a much broader set of mysteries surrounding black holes. Questions that are not merely difficult to answer with current instruments, but that touch something deeper, something about the foundations of physical theory and the structure of reality itself. Chief among them is a question that has occupied physicists for decades and shows no clear sign of resolution. How do supermassive black holes form? The stellar mass black holes detected by gravitational wave observatories are comprehensible in their origins, at least in outline. A massive star collapses. The core exceeds the maximum mass that neutron degeneracy pressure can support. A black hole forms. The mass involved is somewhere between a few and a few tens of solar masses. It is extreme by human standards, but it follows a chain of physical events that can be modeled, tested, and understood at least approximately. Supermassive black holes are an entirely different problem. The ones sitting at the centers of large galaxies today carry masses of millions to billions of solar masses. The processes that produce stellar mass black holes, operating across the age of the universe at the rates we observe, cannot plausibly accumulate that much mass in the time available. You could add up every stellar mass black hole ever formed in a large galaxy, including all the mergers between them, and still fall short of explaining the supermassive black holes we observe. What makes the problem more acute is that supermassive black holes appear to have existed very early in cosmic history. We observe quasars, powered by actively feeding supermassive black holes, at redshifts corresponding to less than 1 billion years after the Big Bang. The universe at that point was young. There had not been enough time, under most conventional models, for black holes to grow to those sizes through ordinary accretion and mergers starting from stellar mass seeds. Something else must have happened. Several proposals exist. Perhaps the early universe produced what are called heavy seeds, black holes formed not from individual stellar collapses but from the direct collapse of entire gas clouds, masses of thousands or tens of thousands of solar masses falling directly into a black hole without passing through a stellar phase at all. If such objects formed in sufficient numbers early enough, they would provide a much larger starting point from which supermassive black holes could grow through subsequent accretion and mergers. Another proposal involves the very first generation of stars in the universe, known as population 3 stars. These theoretical objects, formed from the pristine hydrogen and helium of the early universe before any heavier elements had been produced by stellar nucleosynthesis, may have been far more massive than typical stars today, potentially hundreds of times the mass of the Sun. When these enormous stars died, they may have left behind black hole remnants far more massive than anything produced by later stellar generations, again providing a larger seed from which supermassive black holes could grow. There is also the possibility that the primordial black holes discussed earlier, those potentially formed in the density fluctuations of the early universe directly after the Big Bang, played a role. If primordial black holes formed across a range of masses including some quite large ones, they might have served as nucleation points around which gas accreted and galaxies eventually formed, with the black hole and the galaxy growing up together in a kind of coevolutionary partnership. None of these proposals has been confirmed. Observational evidence for the earliest stages of supermassive black hole formation, the period when whatever seeds existed were first forming and beginning to grow, lies at the very edge of what current telescopes can access. The James Webb Space Telescope has begun probing this frontier, detecting galaxies and active black holes at previously unreachable distances and finding results that are, in some cases, already challenging existing models. Black holes appearing to be more massive than expected at very early cosmic times, growing faster than conventional accretion models easily allow, suggesting that whatever mechanism drives their early growth is more powerful or more efficient than currently understood. The origin of supermassive black holes remains one of the most profound open questions in all of astrophysics. These objects anchor every large galaxy in the observable universe. They have helped shape the evolution of those galaxies across cosmic time. And we still do not know, with any confidence, how they came to be. Then there is the information paradox, which operates at an even deeper level than any question about formation or growth. It is a conflict between two pillars of modern physics, and it has resisted resolution for half a century. Quantum mechanics, the theory that governs the behavior of matter and energy at the smallest scales, is built on the principle that information is conserved. The precise quantum state of any physical system contains information, and while that information may be scrambled and redistributed through physical interactions, it cannot be truly destroyed. This principle is not a minor technical detail. It is fundamental to the internal consistency of quantum mechanics. If information could be destroyed, the theory would break down in ways that would affect predictions at every scale, including scales where quantum mechanics has been tested and confirmed to extraordinary precision. Black holes, by their classical description, destroy information. Everything that falls into a black hole, carrying with it the precise quantum state information of every particle it contains, passes through the event horizon and is trapped forever. When Stephen Hawking demonstrated in the 1970s that black holes are not perfectly black but emit a slow thermal radiation due to quantum effects near the event horizon, this became even more problematic. If black holes slowly evaporate by emitting this Hawking radiation, and if that radiation is truly thermal, carrying no information about what fell in, then when a black hole finally evaporates completely, the information about everything that ever fell into it is simply gone. Destroyed. In violation of quantum mechanics. This is the information paradox, and the reason it has occupied so many of the finest minds in theoretical physics is that both horns of the dilemma seem unacceptable. If information is truly destroyed, quantum mechanics is broken in a way that should have observable consequences elsewhere. If information is preserved and escapes in Hawking radiation, the mechanism by which this happens must involve some departure from the smooth, featureless event horizon that general relativity describes, which creates its own set of theoretical problems, including the firewall paradox discussed earlier. Various resolutions have been proposed. Some suggest that information is encoded on the event horizon and gradually released in subtle correlations within the Hawking radiation over the entire lifetime of the black hole. Others propose that the black hole doesn't fully evaporate but leaves behind a stable remnant that stores the information indefinitely. Some of the most recent and creative proposals involve ideas from quantum information theory and holographic principles, suggesting that the interior of a black hole is not an independent region from the exterior but is somehow encoded in the quantum state of the radiation and matter outside. None of these proposals is complete. None has been tested experimentally, since Hawking radiation from any astrophysically realistic black hole is far too faint to detect with any instrument we possess. The paradox remains genuinely unresolved, a fault line running through the foundations of theoretical physics, visible in the extreme conditions of a black hole where quantum mechanics and general relativity can no longer pretend to be separate subjects. And finally, sitting at the outermost edge of speculation but grounded in real mathematics, there is the question of whether black holes might connect to something beyond our universe entirely. Certain solutions to Einstein's field equations, explored mathematically for decades, suggest that the interior structure of a rotating or charged black hole may not simply terminate at a singularity in the conventional sense. In some of these solutions, the geometry allows for what might be described as a passage to another region of space-time, separate from our own. Whether that other region constitutes another universe in any meaningful sense, whether such solutions represent physically realizable scenarios or merely mathematical artifacts, and whether anything could survive the journey, remains entirely unknown. The concept intersects with ideas from cosmology about whether our universe might be one of many, whether the Big Bang might itself be understood as some kind of transition from a previous state, and whether the extreme physics inside a black hole might in some way seed new cosmic structures beyond what we can observe. Some theorists have speculated that the conditions inside a black hole might allow for the creation of new universes in some sense, with physical constants and initial conditions influenced by the properties of the black hole that spawn them. This is territory where physics shades into philosophy, where the mathematical tools we have are sophisticated but the physical interpretation remains genuinely unclear. What can be said with honesty is that the interior of a black hole, particularly a rotating one, contains geometries that are unlike anything else in the observable universe, geometries whose full physical meaning we have not yet decoded. It is a fitting place to rest for a moment and simply appreciate the scale of what remains unknown. We have confirmed that black holes exist. We have photographed their shadows. We have detected the gravitational waves from their mergers. We have measured their masses across an extraordinary range, from a few times our Sun to tens of billions. We have watched stars orbit the one at the center of our galaxy for decades and confirmed that nothing else could explain their motion. We have observed stars being torn apart in real time and watched the resulting flares light up across the electromagnetic spectrum. And still, we don't know how the largest ones formed. We don't know what happens to the information they consume. We don't know what truly lies beyond the event horizon in any complete theoretical sense. We don't know whether they connect to anything, whether they are endpoints or transitions, whether the singularity is real or a signal that our best theories have reached their limit. For objects we have studied with such intensity, using instruments of such extraordinary sensitivity, this depth of remaining mystery is itself remarkable. It speaks not to a failure of science but to the genuine strangeness of the universe, to the fact that it contains phenomena extreme enough to push every theoretical framework we have built to its breaking point and beyond. The questions that keep scientists awake are not questions born of ignorance. They are questions born of knowledge deep enough to reveal exactly where understanding ends and the unknown begins. And in the specific, well-defined shape of those remaining mysteries, there is something almost beautiful to contemplate. The universe has left us enough to work with to know precisely what we don't yet know, pointing the way forward with the clean edge of an unresolved paradox, the open question of an origin story we haven't yet found, and the quiet interior of an object that has never let anything back out to tell us what it found inside. There is a scenario that occasionally surfaces in discussions among astronomers and physicists, mentioned not as a serious cause for alarm but as a genuine illustration of how strange the universe can be. It concerns the possibility of a wandering black hole, one of those millions of unseen stellar mass black holes drifting through the galaxy with no companion star, no accretion disk, no signal of any kind announcing its presence, passing through our solar system. Under the right circumstances, such an event could occur without anyone knowing it had happened. A black hole of stellar mass, moving on a trajectory that carried it through the outer regions of our solar system at typical interstellar velocities, would be gravitationally detectable only if it passed close enough to measurably perturb the orbits of planets or other bodies. If it passed at sufficient distance, its transit would leave no obvious signature. The gravitational lensing it produced would briefly affect the apparent positions of background stars, the kind of signal that requires careful monitoring of large stellar populations to identify, not the kind of event that would announce itself dramatically to casual observation. It would arrive in silence. It would depart in silence. And the solar system would continue largely as before, its architecture perhaps very slightly adjusted, its inhabitants entirely unaware that one of the universe's most extreme objects had briefly passed through their neighborhood. This is not a comfortable thought, exactly, but it is also not a frightening one in practical terms. The distances involved in interstellar space are so vast, and the cross-section of our solar system so small relative to the volume of the galaxy, that close encounters between stellar mass black holes and inhabited solar systems are extraordinarily rare on any timescale relevant to human civilization. The geometry simply doesn't favor frequent close encounters. That said, the physics does allow for something more dramatic at the extreme end of possibilities. If a sufficiently massive black hole were to pass close enough to the inner solar system, its gravitational influence could disrupt planetary orbits, potentially enough to destabilize the trajectory of Earth or another planet. And in the most extreme theoretical scenario, direct collision between a black hole and a planet is not physically impossible. The probability is vanishingly small. It requires a highly specific trajectory, a specific mass, a specific timing across an astronomical scale. But impossible it is not. A collision between Earth and even a relatively modest stellar mass black hole would be final in a way that few other events could match. The planet would not survive as a recognizable structure. The matter that made up the Earth, its rocks and oceans and atmosphere and everything on its surface, would be disrupted and consumed. There would be no impact crater, no explosion visible from a distance in the conventional sense, just a gravitational event so complete that what had been a planet became part of an accretion flow. It is worth noting, calmly and clearly, that this is not a realistic concern for the foreseeable future. No known black hole is on a trajectory toward our solar system. The nearest confirmed one sits 1,500 light-years away, moving in its own independent path through the galaxy. The scenario of a wandering black hole encountering our solar system in any meaningful way is a matter of probability so low it falls into the same category as most other extreme cosmological scenarios that technically can happen but won't affect anything on any timescale a human society can usefully plan around. What makes these scenarios worth considering is not the fear they might inspire but the perspective they offer. We live in a galaxy populated by millions of black holes, sharing a volume of space with objects we cannot see, cannot track, and in most cases will never know the positions of. The universe we inhabit is not fully mapped. The darkness between stars is not empty. And the fact that we go about our lives entirely unaware of most of what shares our galaxy with us is, in its own way, a quietly remarkable feature of our situation. When humanity first began to understand what black holes actually were, one of the responses was something close to existential fear. If the universe contained objects that could trap light, destroy matter completely, and even potentially swallow entire solar systems, what did that mean for everything we knew and cared about? The fear was understandable, rooted in a genuine encounter with the scale and indifference of the cosmos. But fear, as scientists quickly discovered, was not the most useful or the most accurate response. Because the universe, it turned out, had not simply scattered destruction across its fabric. It had built something more complex and more interesting than that. Black holes, for all their capacity for destruction, are also agents of construction. The same objects that terrified early theorists are now understood to be among the most important structural features of the cosmos, woven into the architecture of galaxies in ways that were not merely incidental but apparently necessary. Consider what we understand about the relationship between supermassive black holes and the galaxies they inhabit. The mass of the central black hole in a galaxy correlates consistently with the properties of the surrounding galactic bulge, the older stellar population clustered near the galaxy's center. This correlation is too consistent, too tight, to be coincidental. It speaks to a deep coevolutionary relationship in which the growth of the black hole and the growth of the galaxy are not independent processes but aspects of a single, interconnected history. When a supermassive black hole feeds actively, its jets and the radiation from its accretion disk pump enormous amounts of energy into the surrounding gas. This energy heats the gas, drives some of it outward, and can suppress the formation of new stars across large regions of the galaxy. In this way, the black hole acts as a kind of regulator, influencing the rate at which its host galaxy grows. Without this feedback mechanism, galaxies and models tend to form stars too quickly and become too massive too early. The observed properties of galaxies across cosmic time match better when the energy output of central black holes is included in the models. A black hole, then, is not merely consuming its galaxy. It is, in a meaningful sense, helping to shape it, moderating its growth, distributing energy through its environment, and participating in the slow, billion-year process by which a galaxy acquires its final form. The monsters at galactic centers are also, in a very real physical sense, the architects of those centers. This is one of the more profound reversals that black hole science has produced. Objects initially understood purely in terms of what they take away, their consuming, trapping, annihilating qualities, turn out to be essential participants in the processes that build the structures we observe. The destructive and the constructive are not opposites in this story. They are the same force, operating in different directions simultaneously. And then there is the long, strange, almost geological question of what ultimately becomes of black holes themselves. Hawking's discovery in the 1970s that black holes are not perfectly black was one of the most surprising theoretical results in modern physics. By applying quantum mechanical principles to the region just outside the event horizon, Hawking demonstrated that the extreme curvature of spacetime in that region causes pairs of particles to spontaneously appear from the quantum vacuum, one of which escapes as radiation while the other falls inward. The net effect, accumulated over time, is that the black hole very slowly loses mass. It radiates. It shrinks. The process is called Hawking radiation, and for any astrophysically realistic black hole, it is almost incomprehensibly slow. The temperature of the radiation is inversely proportional to the mass of the black hole, meaning larger black holes radiate at lower temperatures and lose mass more slowly. A stellar mass black hole in the current universe radiates at a temperature billions of times colder than the cosmic microwave background radiation that fills all of space. Far from losing mass to Hawking radiation right now, such a black hole is actually absorbing more energy from the cosmic microwave background than it emits. It will only begin to shrink through this process once the universe has cooled sufficiently, which will not happen for an extraordinarily long time. For stellar mass black holes, the timescale for complete evaporation through Hawking radiation is already vast, far exceeding the current age of the universe by many orders of magnitude. But for the giants, the supermassive black holes carrying billions of solar masses, the timescale becomes almost incomprehensible in its length. The largest black holes in the observable universe, objects like TON 618 with its 66 billion solar masses, would survive through a span of time written as 10 raised to the power of 100 years before Hawking radiation finally reduced them to nothing. 10 to the power of 100. A 1 followed by 100 zeros. A number so large that the current age of the universe, already 13.8 billion years, is so small a fraction of it that no ordinary comparison does it justice. The entire history of the cosmos from the Big Bang to today represents a moment so brief relative to this timescale that it barely registers. Over these inconceivable spans of time, the universe itself will change beyond recognition. Stars will finish their lives. The last stellar nurseries will exhaust their gas and grow dark. Galaxies will gradually lose their stars to evaporation and gravitational ejection. The cosmic microwave background will cool further and further. Most of the familiar structures we know, planets, stars, stellar remnants, will be gone or transformed beyond recognition. And still, in the cooling, darkening universe, the largest black holes will persist. Slowly evaporating. Slowly shrinking. Radiating at temperatures so close to absolute zero that the difference is almost meaningless. Outlasting everything else that the universe built. At the very end of this process, in the final moments of a black hole's existence, the dynamics change. As a black hole loses mass through Hawking radiation, its temperature rises and its evaporation rate accelerates. The final stages of evaporation become increasingly rapid, ending in a burst of high-energy radiation as the last remnant of mass is converted and released. What had endured for a span of time that dwarfs all of cosmic history ends, at last, in a brief flash. And then it is gone. The singularity is gone. The event horizon is gone. The warped spacetime that had defined that point in the universe for unimaginable eons relaxes back into the background. All that remains is the radiation, spreading outward, carrying whatever information the Hawking process preserves, into a universe so old and so cold and so emptied of the familiar that there is nothing left to receive it. There is something deeply strange and deeply moving about following this story all the way to its conclusion. From the violent collapse of a massive star, or the quieter seeding of the early universe, through the long silent drift in the dark, through the feeding in the jets and the gravitational waves and the slow, patient accumulation of mass, all the way to those final moments of evaporation in a universe grown ancient and still. A black hole is, in the end, not eternal. It is the longest-lived thing the universe produces, but it does end. The darkness passes, eventually, into light. We began this exploration with a simple observation, that even Einstein, the architect of the theory that predicted their existence, found black holes too strange to accept. And across everything that has followed, across the mathematics and the observations and the paradoxes and the images, that strangeness has never fully resolved. It has only deepened, become more specific, more layered, more honest about how much remains genuinely unknown. The nearest confirmed black hole to our solar system is 1,500 light-years away. The light traveling toward us from that distance began its journey when the Roman Empire was still a living civilization. And that object, closer to us than any other of its kind we have found, is still utterly unreachable, entirely invisible under ordinary observation, detectable only through the subtle influence it exerts on a companion star whose movements gave it away. Black holes are the only objects in the known universe that trap light through gravity alone. Every other form of darkness we encounter is merely an absence, a region where light hasn't reached, or has been absorbed, or has been blocked by something opaque. The darkness of a black hole is different in kind. It is not the absence of light. It is the imprisonment of it. The light that crosses the event horizon is still traveling at the speed of light, still moving as fast as anything in the universe can move. And it is going nowhere. The geometry of space-time inside the event horizon is such that all paths curve inward. The light moves at full speed toward the singularity, and that is the only direction available to it. In the entire inventory of what the universe contains, from the simplest hydrogen atom drifting in interstellar space to the largest galaxy clusters spanning hundreds of millions of light years, nothing else does this. Nothing else bends space-time so completely that the fastest thing in existence becomes a prisoner. Black holes are, in this sense, genuinely unique. Not just extreme versions of familiar things. Something categorically different, an object type that sits at the boundary of what nature permits and maps the edge of what physics can describe. After decades of observations, after gravitational wave detections and event horizon photographs and stellar orbit measurements and X-ray surveys and gravitational lensing studies and theoretical frameworks of extraordinary sophistication, they remain deeply mysterious. Not in the vague way that anything complex is mysterious, but in the precise, technical way that means our best theories contain acknowledged gaps, our best instruments leave most of the population undetected, and our best minds cannot fully agree on what happens at the singularity or where the information goes or how the largest ones formed or whether, at some level beyond our current reach, they open onto something we haven't yet begun to imagine. This combination, the known and the unknown held together in one object, the extraordinary detail of what we have learned pressed right up against the hard edge of what we cannot yet answer, is perhaps what makes black holes so enduringly compelling. They are not mysteries in the sense of puzzles waiting to be trivially solved. They are mysteries in the sense of questions at the very limit of human understanding, questions that have already required us to revise and deepen our ideas about gravity, time, information, and the structure of space itself, and that still hold more revisions in store. The universe built them long before we existed. It will sustain them long after everything else it has made has faded. In the deepest dark, in the longest silence, long past the last star and the last orbit and the last familiar structure of the cosmos, something will still be there, bending space, holding light, persisting with a patience that makes all of human history seem like a single breath. And slowly, over timescales no mind was ever built to hold, even those will release their last whisper of radiation and be gone. The universe will have given back everything it borrowed from the light.